That's good. Okay.
Good?
Yeah, so if you stand right here, you'll be in the...
Okay.
Actually, can you bring on one more light? So you're not like the dark Halloween figure? Perfect.
Better?
Yeah.
Cool. All right. How long do I have? Half an hour?
Sure.
All right, we'll go with it. Show of hands. Who had a terrible first car? Come on, like I know a bunch of you did. I totally did. Show of hands if you still drive a total clunker. Yes, Muni does count. My claim to fame is I owned 17 cars in 18 years. All of them absolutely terrible pieces of shit. I actually brought a car with me from Tennessee, and it's still junk. Like I have a project car in San Francisco. Who does that? So some of these cars never ran, because why would they? So this talk, I'm Mike Joy. I want to tell you about some of these stories about the awful junkers that I've owned and what they've taught me about monitoring systems and software. Yes, that is one of my junkers. So there are 4 lessons that I want to cover. Monitoring with antiquated tools is absolutely awful. Systematic instrumentation, though, is pretty awesome. There are really only 3 dashboards I found that actually make sense and are really useful. And monitoring doesn't actually fix anything. I used to own a 1987 Chevy Chevette. Mine looked worse than this. It's hard to believe, but it was pretty bad. If there was a hill and the road was wet, it wouldn't climb it. The dashboard on this car was weird. So you have the speedometer on the left, temperature on the top, fuel on the right, taking up half the dashboard for some reason, and a dummy gauge on the bottom. The dummy gauge was just a light, and like sometimes it went on, sometimes it didn't. But the water temperature is actually the interesting one, because the water temperature right there is also just a light. How hot is the car? Who knows? Is the light even working? Who knows? How would you know? It's just a light, so maybe the light bulb's burned out, which happened on a regular basis. So at some point I decided I needed more instrumentation for this car that barely ran. So I decided I wanted to add another gauge. I wanted to add an oil pressure gauge to this. Now, for those that don't know what they're looking at, which is probably most of you, on the left we have a little thing that goes into the engine block. On the right is a gauge mounts on the dashboard. In the middle is a nylon line. It's like kind of a hard sort of plastic, except it has a tendency to crimp. When it crimps, it cracks. When it cracks, it spews hot oil all over your legs. Ask me how I know. So, using something like this is kind of like debugging your systems with top or SAR, except sometimes it explodes in your face, literally. Have you ever stood up an app without actually load testing it? I mean, I know I have. I did last week, actually. It's a pretty terrible idea. Like, in this Chevette, the engine died. So I was like, all right, I'm going to swap a new engine. And I did it. It worked fine. It started up, it moved, and then I started driving it, and it broke. Transmission just absolutely exploded everywhere. So I'm like, all right, fine, I'll replace the transmission. And then more things started to break, and more, and more, and more, and more, until finally, like, the entire car predictably didn't run anymore because everything had exploded in my face. I didn't even napkin math the requirements of what I was doing. I just kind of said, fuck it, I'm sure it'll work just fine. So I threw it in without really any instrumentation, any understanding of what I was doing, or how much power this new engine would make. This is all pretty awful. Like, it is just terrible. You know what else is awful? I hate Nagios. Like, just so much. We all joke that Nagios isn't actually around anymore, except it totally is. I really hate it. So Nagios is pretty awful, but you know what's actually worse than Nagios? All the homegrown solutions that I know you all have. We don't talk about them because, you know, we're kind of ashamed of them. My favorite was one I ran into when I worked for a national lab called Watcher. Someone explained how Watcher worked to me one day, and it checks the metrics every 15 minutes. Okay, Like, could we increase that? Well, no, it's hard coded in the C library that it uses. All right, fine. But it only checks disk use, memory utilization, CPU utilization, and system load. And every single one of them fire an alert, which goes to email, because of course. And all those alerts have statically defined thresholds. I can't change them, they're hard-coded in the code. And it's the same thresholds for every server, regardless of the function. You know what a better solution to this is? Let's just hard-code the status to say OK on the dashboard. Way better, because the previous, like, what the shit? Like, how can you possibly get anything worse than this? So, yes, everything is pretty awful. If you've got shitty tools, you're really just guessing about performance. So, lesson 1, use better tools. Like, life's too short to suffer with shitty tools. Use something good. At some point, my parents owned this really nice Dodge Daytona, and this was named after a much cooler car from the 60s. This one was not a very cool car. So when I finally was able to buy a car, I'm like, hey, I want a Daytona too, because it was pretty cool, except I had no money. So I ended up buying this one, which is not a very cool car. It looks like shit. And by the way, it wasn't running when I bought it. I had to tow it out. So I bought a car. I spent a lot of time instrumenting it to try to understand, like, what's gone wrong with this thing. Because the dashboard didn't work either. So, like, I'm adding in all this manual instrumentation of, like, hoses and shit into the car, and the instrumentation's mounted up somewhere, like on top of my the hood, and I'm just looking at it as it's running. So my problem was, what instrumentation do I need? And this is kind of a big question, because at the time I wasn't really into cars, but like I kind of understood it. Really, I just wanted to drive something cool. So I thought, well, what could ruin my day? I'll start there. As it turns out, quite a lot. So I started enumerating all the different subsystems of a car, of which there are several. And each of these has a bunch of different metrics. But after a while, it's like, I'm starting to see kind of a pattern. So that got me thinking. At the time, I was doing system administration for a company, and I started thinking, there's some parallels with monitoring software here. So now that I'm looking back on this, and I'm starting to think, like, how would I approach this today? So I have a car that I'm wanting to go, like, the car has no computer in it, so like I need to instrument everything from scratch, but I don't want to do it shitty. So I'm thinking about, how would I do it today? What instrumentation do I need from this car? But with software, you can actually do the same thing. You can be systematic about it. So there are 2 frameworks that I've run across that I've been teaching my clients, and it's worked out really well. One's called Red, the other's called Use. And I can't take any credit for these. I'm not nearly this smart. Red was coined by Tom Wilkie. He's at Grafana Labs. It stands for Rate, Errors, and Duration. So rate, how many requests are going through the thing? Usually expressed as requests per second. Errors is a count of requests that result in errors. And duration is how long does it take to process a request. And these are service scopes. So you might be asking, what's a service? Well, that's a great question. This is just sub-architecture I came up with to illustrate this. We just have a load balancer, we have app service database. The app servers talk to another service with a queue of workers and some external APIs. Pretty simplistic. So what's a service? Well, basically everything where you have arrows. Service it's kind of a wide definition for what's a service. So at the entry point, let's just, as an example here, you would measure requests per second, error count, and request duration right here. And you just do it for each component. And you end up with quite a bit of metrics. You just rinse and repeat. As a side note, don't forget the API. Don't forget those APIs. Like, everyone just assumes you can't monitor the APIs, or they just kind of forget about it and don't do it. Except your application depends on them. So if they go down, you are also going to have problems. So monitor those. So how can you instrument them if you don't control the code? Well, in this situation, you do it at the workers. So every time you make a call out to that API, wrap in a timer or a counter or whatever, and just record those metrics. Easy. So monitor your dependencies is really what I'm getting at. Use is use is coined by Brittany Gregg of Netflix Performance Engineering, and this one is significantly different from Red in that it's resource scoped. So what's a resource? A resource is all physical server functional components, but we're not talking like just CPU, memory, and network. We're talking things like the interconnect on the motherboard. Like that's a resource component. So it could be a pretty big rabbit hole. So use, utilization, saturation, and errors. This is percent utilization over a period of time, like CPU utilization. Saturation, the amount of work left to do, generally a queue. Perhaps the most common example of this would be Linux load. And then errors, just count of error events. Now, not every resource is going to have each of these metrics, and some actually have multiple metrics of each type. Use is really awesome for low-level diagnostics. So, an example for CPU might be percent utilization both per core and system-wide, the run queue length, and cache ECC events. Use is a rabbit hole with a depth you cannot possibly imagine, but it is super useful when you're trying to debug performance. So, especially in like performance optimization or performance troubleshooting, most tools are already gathering a lot of these metrics for you, but I've really found that the best way to use them is using tools like Top and SAR and eBPF, dtrace, things like that. In general, Red is significantly more useful in a day-to-day situation, especially for like alerting and dashboards, things like that. Although I know Sarconis has a fantastic use dashboard. So like, yeah, theirs is awesome. So lesson 2 is, if you can be systematic about the instrumentation, you're not going to miss a lot. One of the biggest challenges I've seen people run into is when they say, what should I monitor? Like, feels like a solved problem, but it really isn't, because the question's really big. You gotta have somewhere to start. So these frameworks are a great place to start. Speaking of which, let's talk about dashboards. This is a dashboard from a modern Camry. Not every car is actually terrible. I'm sorry, I kind of fibbed there. There are a lot of metrics here, but there's an interesting question of why aren't there more metrics on this dashboard? So the average modern car has about 60 to 100 sensors in it. These sensors emit at least one metric per sensor. Some of them emit significantly more than that. So we could have thousands of metrics in a modern car. But if we look at this dashboard, like, there's not that many on here. So what gives? Why aren't there more metrics on this dashboard? The reason is dashboards are a combination of mental models and your current need. I have a pretty good mental model of how a car works. On this dashboard, I see that there's fuel, speed, temperature, lots of stuff that I don't need to know, though. Or there are lots of stuff I don't need to know that's not on this dashboard. A lot of car people complain about the check engine light because, like, it's just a light that comes on. It doesn't tell you anything, except that's fantastic user experience. So going back to the Chevette example from earlier, as I mentioned, this thing only really has a few metrics on it. It's roughly 4. But the bottom is a Subaru WRX, and this has all the things the Chevette has and a whole lot more, all on the dashboards. So what the crap? Why does this one have a lot more? And the reason is because of those different mental models and because of those different needs at that time. The kind of person who drives a Chevette versus the kind of person who drives a WRX looks at the world very differently. They view their cars differently, they're using the cars differently. A Chevette owner is more likely to use it to go get groceries. A WRX owner is probably taking it to the track. So, because they have a different model for how their system, how their car works, and what they're looking for at the time, their dashboards are different. It's presented, it's a whole bunch of different information is presented on this. Perhaps the starkest example that I love is this little gizmo right here. It's called a shift light. All it does is when it's time to shift, it flashes. So that's it. Except this information is already on the dash. So why do I need that? Well, the reason is because when you're on the track going 80 mile an hour around a turn, you don't have the luxury of looking down. All you want is just like a flash of light right here to say it's time to shift. So despite the lesson that I take away from this is there's very little raw data provided, and in fact, it's redundant. This data is already on my dashboard, except it's way more useful to me because of what I need at that time. I only need a single piece of information and nothing more, and it has to be really clear. Which gets me to my 3 dashboards. So there are really only 3 types of dashboards that I've found are really helpful in systems and software. This is New Relic's status page. So this doesn't really tell you a whole lot except the high-level status of each of their different components of the application. It doesn't say what's wrong, it just says that something might be wrong. In this case, everything's great. This is really great for customers because customers don't care about the implementation. They don't really need to know the details of like, oh, Kafka's backed up. Executive and middle management, same way. All they really want to know is, do I have a problem? Is there a problem somewhere that we need to be talking about? At the exact opposite end of this is this random Grafana dashboard I found. This is great for engineering and probably not so much for management because this gets really into the nitty-gritty. There's a ton of information here and it takes a lot of expertise in order to understand what you're looking at. Like, I have this middle graph that shows me HTTP latency. What does that mean? Like, I have all this stuff down here for the different, looks like different endpoints. No customer is going to understand what they're looking at. Executives aren't going to understand, and nor should they. They don't care. It's not useful to them, but it's really useful for engineering. This is just fantastic for debugging. In the middle, which is my absolute favorite kind, is the product dashboard. This one I pulled from MediaWiki's open Grafana system. They have tons and tons of this stuff out there, and it's really cool to look at because like it's their production stuff. So these are really great for like TVs on the wall, and the challenge behind these is that they're very unique to your stuff. So they're hard to create. It requires a very solid understanding of what your service actually is, what it does, how it behaves. So this one, for example, is for their abuse subsystem. So we have, let's see, we have wrong passwords, logins prevented by a block, logins throttled, account creation throttles. So if I'm someone that is working for MediaWiki and I'm looking at this, then if I'm like engineering or if I run this particular product, this particular section of the product itself, then I'm going to understand what I'm looking at. I understand what these things mean. And this is great because you can throw it up on a wall somewhere around the office, let's say next to the team, keep it up on yours, and as you're walking by, you start to benefit from pattern recognition over time. So, assuming that it's kind of washed out, but there's these little green pattern over here, and it's pretty steady. If I'm walking by one day and I just, hey, and like, oh, hey, there's a spike there, that's weird, that's different, because normally it's completely flat. You really benefit from stuff like this. This doesn't tell you what's gone wrong. It doesn't tell you that what the problem is, but it's very indicative of you may have a problem somewhere. These are kind of an early warning system. So lesson 3 is consider your audience and their use cases when you're building these dashboards. So some years ago I bought this. It's an 85 Volvo. It was also terrible. I mean, all my cars are terrible. Except the battery was dead on it when I got it. So I'm like, oh, that sucks. It's been sitting for a while. So I jumped it off and everything was fine. I get it home, next day I hop in, battery's dead again. I'm like, oh, well, that sucks. What crap. So I start replacing stuff, except it keeps dying on me. I'm like, what the hell's going on here? So I had a couple electrical engineer friends who said, you have an electrical problem. We know what to do with this. So we started hooking up all kinds of shit. Just all kinds of multimeters and amp meters and just connecting all these different gauges everywhere to try to figure out at what point is this thing failing. And after a while we had just tons of instrumentation around this particular problem. Except after a while I realized I still don't have a working car. Like, we have all this instrumentation, but I haven't fixed anything. You still have to fix your shit. So I was working for a company some time ago with this PHP app. And the company had this like 3rd or 4th generation engineering team. So the people that wrote the app were long gone, like 10 years previous. So we're talking people who are looking at the application now and going, I don't know how that works. So every time something broke, we say, that broke, we'll just add some more monitoring to it so we catch it next time. Like, yeah, but there won't be a next time. Like, we automated that problem away. We permanently solved that entire class problem. So we're not gonna have that issue again. Like, well, yeah, but just in case we want that there. So you come into this sort of, let's just add more monitoring to the problem. Sprinkle a little monitoring on it, we'll solve the problem. And go 2, 3, 5 years of doing this. And after a while, you end up with, predictably, just shit tons of alerts everywhere. The problem is, you're trying to alert on causes. And alerting on a cause is kind of an anti-pattern, because it's hard to predict causes. In a car, you have this check engine light. All this is doing is it's reading sensor values. It is not making any judgment about the cause. In fact, I started thinking about how this would work, and I came up with this flowchart. And really all this thing is doing is it's receiving a value, and it's looking, is this value out of bounds? And whatever out of bounds means for that particular value. And then it goes to, is the vehicle or driving experience impaired? And if it isn't, then just store the data in diagnostics and move on. But if it is impaired, then now I have a new question. Does the driver need to know which component is impaired? So if no, just show the check engine light. But if yes, show me a specific light. So a good example of this might be your anti-lock brake system. If I'm driving and the roads are wet and I have a light come on for the anti-lock brake system, I'm going to change my behavior. Like, bad things could happen if I don't know that that's broken now. So clearly my car has criteria for what to alert on and how to alert me. So what's your criteria? What criteria do you have for alerting in your software? If something as complex as a car has criteria, why don't we? So my basic criteria, just where I start, is what is this metric or log that I have telling me? What does it actually mean? And this can be harder than it sounds. There are some metrics that you think they mean one thing, but no, like they may mean 2 or 3 things, sometimes all in combination. What action might be necessary as a result of this alert? Think through who is going to get this alert? Why is it going to them? What are they going to do about it? So, and finally, I try to alert on symptoms, not causes. A great example of this might be alerting on API latency becoming higher. Like, this is a symptom, it's not a cause. What causes that? Well, any number of things. But alerting on that symptom tells me about user impact, which is actually what I care about. If you're having trouble thinking of good first alerts, latency and errors are my favorite. Increased latency or increased error rates, fantastic alerts, usually. So to recap, lesson 4, monitoring doesn't actually fix anything. You still got to fix your shit. So, the 4 lessons, monitoring with antiquated tools, it's pretty terrible. Like, just don't suffer terrible tooling. Upgrade your stuff, it's fine. But being systematic about how you decide what instrumentation you need is pretty awesome. It's super, super, super helpful. The 3 dashboards, if you're probably all missing product dashboards, or you have several of them, but you can also be intentional about those. And monitoring doesn't actually fix anything. After a while, you just got to move on and start working on stuff instead of adding more monitoring. So one final parting thought is, it may be fun to drive junkers sometimes, but not when you got to get to work. The same goes for your monitoring. Don't suffer shitty tools just because you've got a job to do. So yeah. So thank you.
I think you wanted to take questions at the end of the...
I can take questions now.
Take them out.
Did you ever figure out what went wrong with the Volvo?
Yes, I did. It is a case of terrible Swedish engineering.
Okay.
The Swedish have these kind of, I don't know what they call them, but the problem is all their circuits are kind of circular. So if any particular point of this thing breaks down, then the whole thing breaks in a weird way. So my problem was that the light bulb was burned out. The bulb that said your alternator or your battery is dead was burned out, which caused the whole thing to stop charging.
So it's like a token ring network.
Yes, it was absolutely terrible.
That's awesome.
So I fixed it with a bunch of duct tape. Yep.
Nice.
So you mentioned having the correct tools, updated tools, things like that.
Yeah.
I overheard you were doing consulting.
I am.
So what are your preferred tools at this time that you like to use?
I recommend, depending on if you have a bias towards on-premise or SaaS. On-premise? All right. Then the Sensu InfluxDB, and for external stuff, this is kind of hard because, like, there's no replacement for Pingdom. Like, Pingdom's awesome. There are several different SaaS apps that do the same thing. There's not really any on-premise. The folks at Grafana have WorldPing, which you can host internally, but it's primarily still a SaaS thing. So, Sensu, InfluxDB, and that takes you pretty far. Oh, and Elk for logging.
I guess one more thing. Have you heard about Sensu 2.0 and the breaking backwards compatibility?
Yes, I was formerly a Sensu partner.
Yeah.
Yeah.
What do you think about that? Do you think it's
I think it kind of sucks for them, but I also understand why they're doing it. Like, they've completely changed the model of how it all works. So yeah, they're breaking backwards compatibility, but maintaining backwards compatibility for what they're doing it'd be pretty hard. From an engineering perspective, it'd be pretty bad for them. Yeah, unfortunately, the upgrade path is not great yet. I hope they change that.
right? That's my major problem at this time.
Yeah, I'm a big fan of Sensu. Sensu 2.0 is going to be awesome, but the upgrade path is just, so they're pushing off the upgrade stuff to either the customer or the partners. So yeah, sorry. Womp womp. Anyone else? All right then.
Cool. So we'll get David queued up next. Sure. Yeah, if you want to do live.
Yeah, I just
Yeah, I mean, some people might go to beers after.
Oh, yeah, I won't be able to say that.
Okay.
Unfortunately.
Okay, we're running ahead of time, so at least time after.
Sorry.
No worries. Cool. So I'm David Gilder. I didn't put my name on that, but I'm the founder CEO of a company called Outlier. We do monitoring. So just to give you a bit of background, we do monitoring. We call it self-service monitoring. We push configuration out to our agents. That means other teams can basically serve the monitoring without the operations team having to do it all for them. That's why a lot of people buy us, because it kind of offloads the work to other people. And we have to do analytics and all the other stuff that Mike was just talking about in his talk. In terms of kind of the background of this talk, we've actually built in the past our own time series database, or we kind of inherited one called TSDB that we were pretty much the only and main contributor to for a long time. We also have, I think it's still one of the top blogs on open source time series databases, so if you guys are interested in all the options out there and all the comparisons and what they do and everything, I don't think it's been updated for a while, so well, it's not open source, I guess, but still, you know, we've got most of the time series databases on that, and we're going to be adding M3DB and what's the other, timescale as well to that. And then last but not least, we're also the founders and run another meetup called Delta Exchange. We've got one in London with about 7,000 members, 200 people come every month for beers and pizza. And then we've got one in San Francisco as well, which is a bit smaller. But actually, if you guys are interested, I know there's a couple of regulars here. The next one's on 25th of October if you guys want to come along and check that out. And you'll see this talk again. So, but there'll be 2 other good talks as well. So anyway, so just kind of a high level to set the kind of thing. So what do we do? So we're a monitoring company. We monitor thousands of servers for large companies like Netflix and Salesforce, all those kind of things. And basically, at the core of it, we have agents that kind of go out there and kind of collect metrics, CPU, memory, but also run checks. So we run Nagios checks, we scrape Prometheus endpoints, all that kind of stuff. Pull metrics into an exchange, put it on a queue, and then to a time series database. So when we started this, pretty much about 5 years ago to almost a day, you know, the core requirements for all of this, you can't have monitoring systems that's less reliable than the system you're monitoring. It has to be scalable, it has to be highly available, it has to be performant. So the first version we ever built of Outlier actually started with React, which, do people here know what React is? Yes? Okay, a few of you. So basically it's a key value kind of distributed store. It's very operationally resilient. That's what we liked about it. You can kind of kill a node and put it back into the cluster, and it will kind of all rebalance itself and stuff pretty resiliently. However, at a certain point, you know, we essentially got to the point where we onboarded some of our first major customers. This was like a year and a bit in, you know. So, and our first major kind of customers came in with several thousand agents, all kind of landing on, and we closed 2 of them in 1 week. So it was kind of like within a 2-week period, suddenly we went from like hundreds of agents to thousands and thousands of agents kind of thing. And so we hit our first fire using React. And like every good SaaS solution out there, we solved the problem with Redis. So we just put some caching in front, and that put out the fire, at least for a little bit. So we kind of cached all the requests and the kind of short-term metrics so that it didn't have to go to the React cluster to pull everything else. However, the first version, you know, so as we got to kind of like 2015, it was pretty clear like the world was going dimensional. So dimensional metrics basically being, you don't just have a metric name, or like Graphite where you have like really long metric names. You kind of pull out all those labels and tags and basically put them in as dimensions into your metrics. So we couldn't really support that on React because it was literally just a key value store. You know, we had like just some keys which basically kind of had the time range and everything, and we could query on those, but it was just kind of like, here's a metric and here's a value kind of thing. And it didn't really have any analytics capability on top of it, so we couldn't write queries to kind of take the average and the mins and the maxes and all those kind of things. You know, it didn't have all that kind of basic functionality you'd expect from most analytics tool. So that kind of caused us to kind of take a step back. So that takes us to version 2. So around 2015, we kind of had to kind of make a decision. So are we going to continue building this on top of React, So we're going to build everything in terms of all the analytics functionality and dimensional data and all that kind of stuff on top of it. But that seemed like a pretty big task for what was a pretty small team at the time. Are we going to buy this? So buy or take in something like InfluxDB or things. We know InfluxDB pretty well, Paul Dix. But at the time, it wasn't kind of at the maturity level in 2015 that we would have needed for a production system. I think React also, before Basho kind of went out of business, they had React TS that came out as well, except they kept dragging us out on the beta program. Like they said, oh, it was coming, it's coming, it's coming, and by the time they said it came, we kind of went in another direction. Or do we inherit, which basically means we take an open source project and we kind of adopt it and we start contributing to it and kind of use that as a starting block. So coincidentally, around the same time, we found this crazy German guy called Heinz. He's based in Berlin, and he's a massive Erlang developer. And as one of his side projects, just in his spare time, he built this thing based on React Core called DB, and it had all this analytics stuff built on top of it. So it's basically kind of what we would have ended up building ourselves if we'd kind of built it, on top of React. It took the great stuff about React, which was you can just set up a cluster and it would rebalance and load balance all the data across the ring, and had all the operational resiliency that we really liked. It had a lot of stuff for kind of write optimization, so you could literally write 3 million metrics a second on a single node into this kind of Dalmatiner box, and it uses ZFS for kind of compression of the data, so we can obviously use terabytes of data to store all our time series metrics. So we got pretty excited about that, and so kind of how Dalmatiner kind of works is it has a query language which is very similar to SQL. There's a query engine that sits on top of a React kind of cluster, and the bit we kind of added later on is that Postgres thing for the dimensional index, because when we found it, it didn't actually have dimensional index, data. It only had just metric names, and you could look those up and do some queries and stuff on it. So it had what looked like a very scalable kind of time series data store. Didn't have the index piece, but we kind of added that on, and then a query engine on top of that. So all built in Erlang, and our developers got really excited about learning Erlang as well. I did lose a bet about we would give up Erlang one day, which we ended up doing. It's not hard to hire for people like that, but it's hard to hire Erlang developers, but it's not hard to find people who want to learn Erlang. Like everyone gets excited about it, but it is a very weird language. So. But anyways, the developers kind of got really excited about that and started basically building a lot of stuff. And a lot of things we actually liked about it was because it's in Erlang, we could hot deploy fixes in real time without any downtime. We could even inspect all the traces in real time using some of the Erlang tooling. It was pretty cool. However, fast forward a little bit, we onboarded a pretty big customer in Seattle, and they were using containers. Around 2015, containers obviously started becoming more of a thing, and so we started seeing these appearing in our kind of customers' infrastructure. And one of the biggest problems of containers is this thing called series churn, which I'll talk a bit about later. But essentially, every time a container appears and then disappears, let's say each container collects like 50 standard metrics, CPU, memory, load, that kind of stuff, and then that disappears and another one comes along. Well, that's actually another set of another 50, metrics kind of thing. And so that keeps happening again and again every single time you switch on and off containers, and all of a sudden your index basically starts growing infinitely kind of thing. So we kind of built this kind of add-on to Dalmatiner, which was this Postgres index that essentially would allow you to kind of query all your metrics and select on tags and dimensions and all that kind of stuff. But then because of the series churn problem, the first kind of problem, the first issue we really hit was as more customers started adding containers to infrastructure, this index just went from hundreds of thousands of rows to millions of rows to hundreds of millions of rows, and we were just constantly, we were actually at one point just running manual jobs to delete the index and just let it recreate itself again, just so that people could still kind of query their indexes and get their metrics out. So we were getting, at worst case in this case, it was like 20 seconds, to query a metric, and it wasn't because of Dalmatiner, it was because the Postgres index was just so big that it was taking 20 seconds just to look up what metrics it needed for a query before it could kind of go and fetch the actual time series from the Dalmatiner metric store. So we did solve that problem, and the way we solved that problem was essentially similar to Prometheus 2.0 and what they kind of introduced into their second version of Prometheus, which is basically partitioning the index by time. Because when you query time series, you don't need to fetch every single metric that you've collected since the beginning of time. If you're doing a range query for a 2-hour period, you only need to collect the indexes for that 2-hour period. And so we managed to solve that issue with the index. However, later down the line, we had another fire. So we actually had a few more big customers join us, and then we were monitoring at a much higher scale than we'd ever monitored. Because we're a startup, kind of growing, and big customers are kind of joining us. And so we had a second fire, in the sense of some of our dashboards were kind of grinding to a halt. Some of our customers were using us for capacity planning, which meant they were doing range queries over several months and having to pull data across several months. And some of these dashboards, for whatever reason, had like hundreds of graphs on it. So they were pulling I think the worst dashboard I saw was like 10,000 time series metrics being pulled onto a single dashboard for a 2-month period. So that was I think it was like 10 million data points or something like that in raw form. And Dalmatina stores all the metrics in raw format before it kind of rolls it up and does all the aggregations and stuff like that. So okay, I've got the slides wrong. So I just talked about how we solved the indexing thing. The third one. So what we kind of learned with this one is we kind of got ourselves into another scale, that we, as a company grew, and we were struggling to keep up with some of these really big dashboards and some of these really big customers and stuff like that. And one of the lessons we kind of learned is, so if you look at the time series database blog we did, which I put at the beginning, if you go there, it kind of goes through all the different time series databases, and obviously at the time when we were evaluating Dalmatina wins, because we could write 3 million metrics a second to a single node. It turns out writing is pretty easy. You could take a file and write a program that just writes out 3 million metrics in a second, kind of thing. The hard bit is reading. So querying this data, what was actually happening is, because of the way we're storing the raw metrics in Dalmatina, and because Dalmatina doesn't push down queries to each of the nodes and then pull them up, it literally pulls back all the data to the query engine. We were getting, for some of those dashboards, like the one I just talked about, it was taking 40 gigabytes of network traffic just to pull all these raw metrics back, and essentially then the query engine would process it in like a second. It was pretty fast to query once it was in memory, but to pull all that stuff off disk into the network, we were getting loads of network limits and I/O problems and stuff like that, and we started pulling all these metrics across the entire cluster, and reading became a really hard problem. And so we went through so many things to try and optimize the reads, the way we're storing the data, compressing the data, all this other stuff, before finally we just essentially didn't give up. We solved it, but it was solved in the old-fashioned way of just sharding out customers. So we literally had to just split out all our customers. Before that, we were all on like one big Uber shard, which basically, which was good from an operational point of view, because we only had one shard to manage, and we had a small operations team of a couple of guys. We didn't want to have clusters and clusters and clusters of these things. But the only way we ended up solving it really was by taking all our biggest customers and putting them onto their own dedicated shards. So at least their traffic wasn't interfering with other people's traffic on the same cluster. So eventually we kind of got there on Dalmatina, but what we realized over that 2-year period is building a time series database really sucked. And when I looked at kind of our engineering kind of stuff, like as a software as a service company, as a monitoring company, like as a CEO, like I want to see my engineers innovating, building features, all that kind of stuff. I don't want them spending 90% of the time, which was kind of happening at some points, scaling a time series database. Like that's not a differentiator for us. Everyone needs it as a table stake, but having a time series database, everyone has a time series database in the monitoring kind of space. And you could argue there's some stuff you could do in that space. Like some people have done some really cool stuff in it, but really customers don't care. They want to see their graphs and they want to see them quickly, kind of thing. And so we kind of got to the point around 2016 we were like, I think Dalmatina, not to knock it, if you're using it for like just a single tenant, or you're just using it yourself for like a few hundred servers, maybe a few thousand servers, you'll find it's probably okay, because it does scale. We've fixed most of those problems. But I guess one of the issues is, being the only user of this time series database, we were hitting all the problems as our scale increased, kind of thing. So we were having to firefight, you know, I can't even imagine what the next issues would have been. You know, we would have 6 months down the line, we'd hit another scale, and then we'd be firefighting next issues. And our engineering team was just getting sucked into this. So, you know, it was a really hard problem. So we eventually decided to move into another architecture, which I'll talk about later. But I'll kind of talk about, you know, why time series is hard, and actually why some of the stuff about time series actually makes it a bit better as well. So the number one problem that's happening right now, most monitoring tools is, as a Tourist BIG once said, more services, no problems, more metrics. You know, as we've kind of moved into cloud and containers and into microservices, you know, just the number of metrics we're just collecting is just going up exponentially. This is why monitoring's become a hard problem. You know, it isn't, you know, you can't just put one single InfluxDB thing there for, you know, a sizable estate. You need to start building clusters, and, you know, I know everyone that's used any graphite's probably gone through a massive scaling exercise at projects, you know, to try and make a scale once you get to a certain size and all that kind of stuff. It's just getting worse and worse every day, and this is going to continue going up as we add new architectures and new things and serverless and all these other things, you know, just generating more and more metrics. The other thing is, you know, as you get more metrics, you get more cardinality. That means your indexes are way bigger. So, you know, our average customers now are collecting like 3 or 4 million metrics, you know, at any one time kind of thing. So, you know, that's a high number of metrics you have to query and stuff like that when you're kind of, you know, kind of monitoring all these different services and having all these different labels and dimensions on them. I already talked about kind of series churn, so containers make it even worse because you're literally just churning metrics every, you know, like I said, this actually was a report we did on the version 2 time series database. When we're having all those issues with the series churn, we were kind of looking. We had one customer that was cycling containers every 6 minutes on about 100 nodes. That was like, it was basically a lot of metrics coming in, and most of those metrics were living for like 6 or 7 minutes, and then another load was coming in, kind of thing. And so that series churn really kind of kills you in the time series space, you know, especially as we move to containers and things like that. And then to make things even harder, I kind of took a quote from Amy, because she talks about this at Pinterest. You know, she says, performance, do whatever it takes to make it fast to get developers to kind of adopt this. You know, I would say there's an issue with end users in the sense of, you know, we're all used to instant search results of Google. We're all used to instant gratification. And so everyone kind of expects, oh, I can just dump whatever metrics I want. I'm going to write this, you know, stats.d or Prometheus endpoint, just dump 100,000 metrics in there, and then I just expect everything to query like in sub-second response times and stuff like that. And so because of that, that makes this a really hard problem because the user expectations are, if it takes 2-3 seconds or something to load a graph, sometimes, you know, sometimes they will complain. They'll definitely complain at 10 seconds. You know, so you have to kind of be able to do this in a super fast performant way, but there's a cost to that. And then remember, just like at the beginning, it has to be scalable, available, performant, blah, 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 all that kind of stuff. However, the good news to all of this stuff is, you know, one of the things we've kind of learned along the way is, and there's lots of blogs that can kind of confirm this, most queries are actually in the last hour. Like when you actually look at most monitoring tools and kind of how people use them, they're not really using, you know, we store 13 months by default, we can do longer. Most people do about 13, 15 months in the SaaS monitoring space. But actually, if you look at the majority of queries, they're probably all in the last hour, because everyone's looking at the current data. You don't really care so much about last week, you know, unless you're kind of doing some capacity or, you know, just comparing week on week and that kind of stuff. The other thing about time series data is writes are sequential and mutable. That means, you know, we don't, you know, we're not going in there and having delete functions to kind of go and delete stuff or update, you know, a time series value that was recorded 2 hours ago or something like that. We're just sequentially just appending and adding time series data points, you know, in a constant stream kind of thing. And the other thing as well, kind of related to that, is it doesn't have to be, I kind of put ACID there, you know, like ACID databases, where they have to be transactional and you have to guarantee rights and all that kind of stuff. It doesn't really matter in the monitoring space. You can afford to lose a handful of data points. You know, like it's not going to affect your visibility if, you know, you lose a couple of data points here and there. You know, so that means you don't have to build this most transactionally resilient database that can store every single thing and guarantees that you're going to write everything. And I would argue one of the reasons why more general time series databases out there, like who are trying to cater not just for the operational use case where we don't care about a couple of data points here and there, and also maybe the financial service use case where they have to store every single transaction, that kind of stuff. like where they hit the scaling issues, I think is mainly because of this, because they're trying to cater for both use cases and trying to store everything, and that does make your architecture a lot more complicated and harder to scale. And then also the other thing as well is reads are kind of defined across a defined time period. So you're not trying to you don't have to search everything. You're like I said, most of the queries in the last hour. So it's easy, so it makes it easier reading problem to kind of find the data and stuff because it's in a time box kind of area. And then the last thing is, Gorilla DB kind of did a lot of papers on this and stuff like that. The data is actually quite easy to, well, not easy, but there are some really good techniques you can use to kind of compress it, because most of the time series data out there isn't changing that much, kind of thing, and you can take advantage of that. So that means you can shrink the amount of data, you still collect the same amount of data, but you can shrink the amount of storage you actually need to kind of keep this data on disk and in memory and all this other stuff, which is what Gorilla DB from Facebook. Do you guys know that? Yeah, so they did a really good paper on their kind of compression algorithm and stuff, and we've actually used some of that ourselves. So it's a really hard problem, but there are some things about time series that make it easier, and especially when you look at time series from the use case that we care about, which is operations, which I guess is what everyone here is here for. If you don't have to worry about every single data point and you're looking mainly for trends and all that kind of stuff, it does make the problem somewhat easier. So we kind of took a step back at the end of 2016, and we were like, we can't carry on, building a time series database. We need to have this. This is table stakes as a monitoring company, but we want to spend less resources on that and more resources on, alerting and all the other things that we're also building as well. And so we kind of, having learned the hard way how to do this, we kind of stepped back and took all our lessons learned, and we were like, okay, if we had to do this again, what would we do? So one of the things is, well, we don't need to put this all into one database. We don't need to put this all into one process, one service. The Delma team was designed to be an open source project. In fact, all the open source time series databases are designed this way because they're designed to be installed by someone else to run them on their own data center. They're not designed to be run with 30 or 40 different microservices where the installation docs is install this, install that, or maybe with Kubernetes it's like the big manifest file. They're all designed to be kind of easy to operate. And because of that, that means that, some of them do split out some of the processes and different, like the query engine may be separate from the time series store. But, if you can take it a step further, in the SaaS world, our customers aren't running it, we're running it. So we could actually take the advantage of, well, actually we can split everything out. The entire process could be different services that we basically run behind the scenes. The customers don't care that, we're using like 10 different services to run this time series architecture. And that way we can independently scale each part of it and, easier to kind of fix, different things without having to worry about everything being in one code base and easy to install on one server. So the first thing we did was kind of split it out and start unbundling all the services. The next thing we did is we went back into the kind of sphere of open source time series databases and stuff like that, and we were essentially evaluated all of them again. We looked at Gorilla DB, we looked at a whole bunch of them, and the one we kind of settled on was Atlas from Netflix. Hands up if you guys have heard of Atlas from Netflix. Okay, cool. So a bunch of you. So Netflix basically uses this for I can't remember the exact number. I always say 3 billion metrics a day, but my co-founder keeps saying it's 1.3, and I don't know where it is exactly now. But essentially, it's a lot of metrics, and they've got thousands of engineers that rely on this every single day. All their monitoring tooling is built in Atlas. It's in memory, so it's super fast. It's got a really rich query language on top of it, so you can do all the kind of analytic stuff you'd expect from like Prometheus or Grafana or Graphite, whatever. All that stuff's possible on top of Atlas. And the sensible limits is the other thing as well. That was another lesson we kind of learned along the way. We did start this a little bit naively, like unlimited metrics, unlimited this, and and no limits on number of dimensions, and no limits on this and everything. And that also created a few problems for us as well when customers abuse that. But it has some sensible limits in there. So sensible limits, for example, are if you do a query that returns more than 1,000 time series in the data response, it's going to give you an error saying the query is too broad, like reduce your scope of your data. Why? Because on a graph, you're not going to be able to look at 1,000 lines and really see anything. So it's kind of useless to have more than 1,000. So they put some limits in there to kind of protect the system from people doing, like a wildcard query that would pull back all the metrics and time series and stuff like that. So things like that, they've kind of gone through this themselves. And the key thing for me, from kind of a CEO perspective, was they'd already got this to a scale that was, bigger than most people are running at. They'd already hit all those scaling challenges along the way. So we were taking something that had been already battle tested at a much bigger scale and was being actively maintained and stuff like that. I don't think a lot of people are using Atlas outside Netflix. And I think the key reason for that is it's a component. It's not a standalone time series database. You could put it on a server and start pushing metrics into it, but actually if you want to use it in production, you need to build a lot of tooling around that, and I'll talk about what we had to build around that. The second thing is, knowing that the value of data kind of goes down exponentially over time. We basically built a multi-tier architecture. So we actually store all the raw data that comes in instantly available in memory, it's read off memory in a short-term store. That's the M1 there. That stores the first 6 hours of data, because generally most of the queries we've seen are less than 6 hours. So you go in there, you can kind of do a 6-hour query. It's just going to be immediately available, super snappy, super fast. M2 and M3 is like the 2-week storage, and then the 13-month storage. They're still super snappy, by the way. But because it would be really ridiculously expensive to do everything in memory for a 13-month period, we've actually adapted Atlas. It's something we will hopefully contribute in the future. We've now built another storage engine for it, which is a disk-based storage system. So actually very similar to the Prometheus 2 kind of data force structure and stuff, and how we store indexes and metrics and stuff on disk. But still super snappy and stuff like that. But generally, we don't see a lot of people touching that data, so we put it in cheaper kind of disk-based storage and stuff. And that's also where we do our roll-ups. So raw data is on M1, 5-minute roll-ups for M2, and then 1-hour roll-ups on S3, which is the long-term storage. So we kind of split it out to different tiers. And then, of course, learning the hard way, we put sharding in from day one. So all our big customers go into individual shards, but then we have smaller customers that pay us, $50, $100 a month. They all go into like an Uber shard, and then we shard them with keys and stuff inside that shard. So we don't have to, because a shard can cost a few $1,000s a month on AWS to host sometimes, depending on how big it is. So basically sharding's built in, and then even beyond that, how do you shard a shard? How do you scale a shard? All these nodes are kind of organized into groups, and we have a hashing algorithm that essentially takes all the metrics and basically hashes them into an algorithm that essentially means that we know where the data is stored, because we've got rid of, the other thing I forgot to mention, we got rid of clustering. Atlas is not a clustered database. It's all in memory. It's single node. When you have to do stuff to query it, which I'll talk about in a second, but essentially there is no clustering in it, because clustering causes a lot of noise across the network. It makes the problem actually much harder. So by storing everything on individual nodes, what we actually do is we query those nodes individually. We have mirrors. If one node goes down, we still have another node as a backup, and we also have a way to reload nodes in memory in about 2 minutes if one of them goes down. And that actually happened to us a few weeks ago. It was perfect. No one woke up. It just reloaded itself and all that kind of stuff. And we do that using S3. So I'll come back to that in a second. And then finally, now you've got all these shards and nodes and groups and all this kind of stuff. How do you query it? Well, we have this service called Blend. Essentially uses the same kind of sharding. So we use console to kind of say what shard is for which customer and where all the metrics are organized. So essentially uses console to do the reverse, like where are the metrics when you send in a query, and then it will basically query all the nodes that need to be queried, pull up the queries are pushed down to the nodes to actually get the aggregated metrics back from each node, and then it just blends them together if it's across periods or across nodes, and then basically pushes it back to the user. And it does that really, really fast. So when you kind of put it all together, you get something like this. So this is now our kind of version 3 architecture. I'll kind of walk around here. So you can see we still have that agent exchange where all the agents connect to and kind of push metrics in. We use Kafka now for our queue. We used to use RabbitMQ, but RabbitMQ really doesn't scale at a certain point. So we use Kafka to kind of do that. And then we've got these 2 services. One's called Pump and one's called Dump. Pump basically pushes everything into the kind of in-memory Atlas time series database in real time. So they just come on the queue, just pushes it in, and that's immediately available to query on dashboards, alerts, and all that kind of stuff. Basically dumps it all onto S3. So that's our separation of tier. Because the other thing as well about time series databases, incredibly hard to back up. Well, at least when you're doing it at a certain scale. So instead of trying to back up time series database and stuff like that, we basically we dump all the raw metrics into S3. That means we can always replay metrics at any point to reload databases and all that kind of stuff. So we actually had an issue a couple of weeks ago where our long-term storage has a bug in it, it failed. We basically fixed that bug, and then we just reloaded all the data in like, I think it was about 30 minutes from the S3 bucket. So S3 is our kind of backup, and it also creates that separation of concerns between the short-term and the long-term storage. So basically everything gets dumped into S3, and then basically on an hourly job, we have a map-reduced job that essentially goes in and basically just starts churning them out and pre-computes all the rollups for the medium-term store and the long-term store, and basically puts it into the Atlas node, which you've got the disk space storage that we built for Atlas. And then across the top, you've got the blend, which basically, if you're doing a 1 hour query, it's just going to go to these two nodes, it's going to merge the results and also double check that they're both consistent, all that kind of stuff. So you have to do consistency checking because we don't have clustering anymore. And then if it's a longer query, it will fetch some of the metrics from here, some of the metrics from there, and then blend them together. So we've got so from a user perspective, you're just making a query, and then behind the scenes, it's basically figuring out where it has to go in this architecture. And this is a single shard, by the way, so we can replicate this for different things. They're all in auto-scaling groups, that's what the blue line is. So essentially when a node goes down, we have a CloudWatch thing that just basically kicks it off again and then spins up a new node. And then, and actually we're moving the MapReduce job to a Kubernetes job because it's much faster and we can process things a lot quicker. So that's kind of where we ended up, and we're actually super happy with it. Like literally, we've gone from kind of constantly firefighting to now in the last, this has been running for about 12 months now. Like I said, we've had issues like everyone. We've lost nodes, we've lost time to. We even lost the long-term storage tier a couple of days ago, just for a couple of hours. And all of that stuff just healed itself with auto-scaling groups and the S3 stuff being that source of truth that we can always go back to if we need to restore and recover people's data. So it's a really resilient architecture. This is actually based on a lot of stuff that Netflix has actually built internally using Atlas as well. But they don't open source all that stuff around it. They just open source the orange Atlas stuff. So you still have to build this stuff if you were kind of using Atlas. So, kind of in conclusion, building a time series database is hard, and it's only getting harder because the number of metrics is going up exponentially. This is one of the hardest problems we see when we speak to any of the large companies around here. Just storing and building time series databases and stuff is really hard. It does hit a full-time job. Most of the companies we meet, they have dedicated people sometimes that just basically are just responsible for scaling and maintaining their monitoring infrastructure because it becomes a full-time job at scale. There are a lot of open source solutions out there, and we've met some really cool ones like M3DB from Uber. They recently open sourced that a few weeks ago. But there's no perfect solution. Like M3DB, they solve the scaling problem by pre-aggregating all the metrics that go into the database. That means you kind of need to know the rules to aggregate before you put the data in. Well, we're a monitoring company. People just want to send us the data, and then they wanted the aggregations on the query. So it didn't quite work for us. But they have some other cool stuff, and they're doing it at a very big scale as well. So obviously I'm a vendor, I know, but I would generally say, regardless of us or whoever you go with, like if you have the money, buy it, don't build it, because it is a really hard problem to solve when you get to a certain scale, So that's our kind of journey, and that's kind of where we ended up, and a kind of background on time series databases. So that's it from me. Any questions?
You mentioned that if one node goes out, it takes like 3 minutes to reload the data back to the cache. Did you consider double write data from top?
Oh, it does that. So we have 2 mirrors, and then basically, it's double writing to both of them, basically. And then, so it's only like one of the other nodes goes down. You still have one so people aren't affected, the end users, but then we obviously have to restore that one to make sure it catches before the other one goes down. So, yeah.
So you mentioned Atlas is single node, and you don't have any clustering there. Are you just persisting different metric streams to different nodes, and then doing like a fan out to query?
Yeah. So we have this kind of hashing sharding algorithm. It's pretty simple, to be honest, but it just basically, means that the same metric goes to each of the same nodes and stuff. And I think because of through console, it's very dynamic. They spend a lot of time building on top of console. As you add new nodes and stuff like that, and your scaling groups go up and down, it kind of adds to that console kind of configuration. I don't know all the details of it. The engineering team back in London built it, but from what I understand, the hashing algorithm adapts itself as more nodes are kind of added and removed in the cluster kind of thing. And so yeah, so basically, the query that you're doing may have metrics that are spread on several nodes or groups inside that shard, and the blend basically knows with console where to go and get those metrics using the hashing algorithm, and then basically pulls them back and then blends them all together into one. So you need that blend layer at the top to kind of do the queries.
When you're sharding, do you use multiple pipelines, one single pipeline, but just sharding catalysts?
So Kafka. So yeah, another good question. I probably should ask them for more detail. I know we use a lot of partition. I know we use several topics. I don't know exactly, but yeah, I think actually they're using Kafka partitions for certain customers and stuff like that. We haven't got to the point. Kafka is actually pretty scalable, so we've got to the point now where we can put so if there was a single point of failure, I guess, Kafka's clustered, but it would be the Kafka piece, where essentially, all the customer metrics coming into one Kafka cluster, and then we're kind of pushing stuff out to all the shards from there, kind of thing. So, I don't know exactly how they scale that. I assume there's a lot of partitions in it. Yeah. Okay. So.
You mentioned that you're using Atlas. Have you considered any other alternative solution, like why Atlas wins over other solutions?
Yeah, we've been through all of them. So I think InfluxDB is great. It's just, I think at a certain scale it does, it gets harder to kind of manage and stuff. And so essentially for our scale and all that kind of stuff, it wasn't really a good fit for us, especially back in 2015 when we first evaluated this. There's some new ones that we were really interested, like with M3DB when it came out. Not that we were going to switch, because it only came out a few weeks ago, but we did meet up with those guys to kind of find out more, just because it looks pretty cool and we're interested in this space. But like I said, I think the really hit home, like the pros and cons that you have to make. They've done it in a way that works really well for them, and for some people that's going to work really well, but for us, because everything's pre-aggregated, that wouldn't work so much for us, but that's one way of scanning things. Instead of storing all the metrics, pre-aggregate them, roll them up, and push them in, after that, kind of thing. It's another way of solving the same problem. But there's lots of solutions out there, and I'd say go to that blog that I showed at the top. So just go to outlier.com, go to the blog. We've got a search thing as well, top time, or even just Google top 10 time series open source databases. We become result number 1 or something. And there's a full list of pretty much everything there with comparison spreadsheets. Only missing, as far as I'm aware right now, M3DB and timescale. Those are the two we haven't included yet. But yeah, there's a lot out there, but there's pros and cons to all of them.
So you mentioned that you wrote a new backend driver for Atlas to store disk-based backend store solution. Why would you do that? One of the problems with Prometheus is having a bunch of different file servers, and you have to aggregate it, federate it, or whatever. Since here you have a backend storage in S3, and then you have in RAM storage in Atlas, why are you writing a disk-based solution?
It's to do with cost. So essentially, in that tier we're only storing 6 out. So I think we can get about 2 million metrics per node, and then times that by the cost of an EC2. I forgot the size. Actually, I think it's written on that. It's an R4 2X large. I can't remember what that is per hour. Reserves, whatever the cost is for that. So you can imagine, like 2 million. That's our kind of short-term kind of resilience in memory. And we actually, one of the things that we can do, which we do for some large customers, we have a lot of flexibility. Because of console, we can configure different shards to have different retention periods and different things. So if a customer did say to us we only want 4 weeks of full resolution metrics, we could do that for them just on their shard. So we kind of do that all in memory in the short term, because that's what most of the queries are in the last hour. So you want that to be super snappy. I'm troubleshooting. I just want the graphs to be boom, 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 on the screen. But then for the other stuff, because we know it doesn't get touched, everyone wants it because just in case, But it's like most of the time, they don't touch it. If we had to store that in memory, with that kind of 2 million per node and all that kind of stuff, like that would be a very, very expensive solution. We'd price ourselves out of the market. So for that one, we had to develop this file-based stuff, and it's still fast. I'm using it for my son. It's on the Uber shard, but my son's got a science project with Raspberry Pi measuring air pressure and wind speed and stuff like that. We used Outlier. I did a nice blog about it in a couple of weeks. And so we're pulling back several weeks of data to kind of show on his science project and that kind of stuff, and it's still fast. It's just not as fast. We're talking like still fast, but it's not as fast as in memory kind of thing.
You probably don't care if it goes away because you're still seeing all the data goes through.
Well, yeah, that's the thing. So this was actually another thing, because we had problems in Jalopies. We couldn't back it up because the amount of data coming in. By the time you finish the backup, when you're like terabytes and terabytes of data, like it's changed. It's like more data's kind of come in and stuff. So we were taking snapshots and we were doing other stuff, but it just wasn't very scalable once you get to a certain size. And so essentially we couldn't solve that with Dalmatina. But when we kind of split out all the components into different tiers and different services, S3 became that durable, cheapish kind of backup storage. And the other kind of advantage for us as a monitoring company is we're starting to do stuff around machine learning and things like that. Like we now have this massive pool in S3 where we can use Athena and Redshift to start doing data science and stuff on all these kind of metrics. And actually the team are really interested. Another kind of use case that they want to build at one point is maybe at some point, all this stuff is kind of real time in memory and stuff like that. But if you want to do advanced reports on the raw data for 13 months, like we could give you access to a bucket with a secure key, and then you could write your own Athena queries or Redshift queries on your own data to kind of, do like long-term reporting on it. Because we still have it there, we don't actually get rid of it. We in theory we're supposed to get rid of it after 13 months, but we keep it because we want to do advanced algorithms and stuff one day, and that data is quite valuable for that. So yeah. Okay. Well, thanks. Don't forget 25th if you're interested in another meetup. We have our meetup at Amplitude, and thank you.
Thanks to Craigslist for hosting. Appreciate it again. And I think if folks are interested, might grab a quick beer down at Irish Bank down there. We don't have any speakers scheduled up next, but if anyone's interested in talking, go ahead and ping me through the Meetup app, or send me an email, fredmoyer@gmail.com.
Surely they'll disable the inbound email at some point.
It doesn't work too well already.